To the first part of the lesson on Taylor and Maclaurin series. So Taylor series, we have the following theorem. If a function has a power series representation at a, for example, if we can express our function f of x as the sum n equals 0 to infinity of c sub n times x minus a to the n with radius of convergence r, then the coefficients are given by the following formula. So c sub n is equal to the nth derivative of f at a divided by n factorial. So a different form of the Taylor series, which we're going to look at below, is if you were to expand out that sum term by term. So if n is equal to 0, the first term would just be f of a, right? You're not taking a derivative. You have x minus a to the 0. 0 factorial is 1. Plus, then the second term would be the first derivative at a times x minus a to the first divided by 1 factorial. Plus, and then you have the second derivative at a divided by 2 factorial times x minus a squared. So everything matches. The level of the derivative, the factorial in the denominator, and then the exponent on x minus a. And this is a Taylor series. Now, when a is equal to 0, so when your power series is centered at 0, it's called a Maclaurin series. So special case of a Taylor series. These have so many applications in mathematics, so the basis for understanding this is really important. Now let's look at an example. So find the Maclaurin series for f of x equals the natural log of 1 plus x and the associated radius of convergence. So we're going to use the formula here. The function f of x is natural log of 1 plus x, and since they told me to find a Maclaurin series, then that means a is equal to 0. So how do we begin the process? Well, we need to figure out what the coefficients are, right? So I'm going to compute the nth derivative of my function at a, or of x for now. Then I'm going to substitute in 0, and then I'm going to put it all together and figure out what the coefficient is. So it's going to be the nth derivative at 0 divided by n factorial. Okay, so let's make a little table. And the process is you compute enough derivatives, fill this in, build the coefficients until you see a pattern, and you can write it in sigma notation. So here we go. We're going to fill in the first column first. So the 0th derivative, or the original function, is just natural log of 1 plus x. And then the first derivative, we know it's going to be 1 over 1 plus x. The second derivative, well, that's 1 plus x to the negative first, so it's going to be negative 1 over 1 plus x squared. The third derivative would be negative 1 times negative 2 over 1 plus x cubed, and the fourth derivative is going to be negative 1 times negative 2 times negative 3 over 1 plus x to the fourth. I wrote it that way so you could kind of see the pattern that's emerging. Okay, now I'm going to evaluate each of these derivatives specifically at 0. Since we're finding a Maclaurin series, a is equal to 0. So natural log of 1, that's 0. 1 over 1 plus 0, that's 1. I'm going to have negative 1 over 1, which is negative 1. This is going to be positive 2 over 1, which is positive 2. This is going to give me negative 6 over 1, which is negative 6. So notice it's alternating. And then what would the overall coefficients be? So you're going to have this value, and then just put it over n factorial. So 0 over 0 factorial, that would be 0. Then we have 1 over 1 factorial. This would be negative 1 over 2 factorial, 2 over 3 factorial, negative 6 over 4 factorial. Okay, so let's see, what are we going to be left with here now? I want to put everything all together and list out the first few terms. So my function, which is natural log of 1 plus x. The first term is 0 over 0 factorial times x to the 0 plus, then I have 1 over 1 factorial times x to the first plus, then the next term is negative 1 over 2 factorial times x squared, right? X minus 0 squared. I'm getting all of these values from here. Then I'm going to have, what's next? Plus 2 over 3 factorial times x cubed plus negative 6 over 4 factorial times x to the 4th plus so on and so forth. Okay, now can we clean up a little bit? Well, let's see here. This first term, this is just 0, so that's gone. Then here, this is just 1 times x to the first. Then I have negative 1 over 2 x squared plus 2 over 3 factorial. The 2 is going to cancel out, so I just have 1 over 3 x cubed. 4 factorial is 4 times 3 times 2, so the 3 and the 2 is going to cancel with the 6, so I have minus 1/4 x to the 4th, etc. So this looks like a pretty simple pattern, right? I could write this as the sum, starting at 1, going to infinity. Notice I always have n in the denominator. It's alternating, right? And I want the first term to be positive. So I'm going to have negative 1 to the n plus 1, and then x is raised to the nth power. All right, so there is our Maclaurin series. Now, we need to find the radius of convergence. So how do we do that? Well, in this case, I'm going to use the ratio test. So I need the limit as n approaches infinity, absolute value. I'm just going to throw out the negative 1 to the n plus 1 portion since I'm taking the absolute value. So I'm going to have x to the n plus 1 over n plus 1 over x to the n over n, which is going to give me the limit as n approaches infinity. And here we have x to the n times x over n plus 1 times n over x to the n. Okay, so that x to the n cancels out. And then I can take the absolute value of x outside the limit, right? Since the limit is as n is approaching infinity. So I can write this as the absolute value of x times the limit as n approaches infinity of n over n plus 1. As n approaches infinity, n over n plus 1 is going to approach 1. So this limit is equal to the absolute value of x, which I set strictly less than 1. So what does that tell me? My radius of convergence is equal to 1. All right, good. Let's look at another example, this time centering it somewhere else. So here in example 2, we're going to find the Taylor series for f of x equals cosine of x centered at a equals pi and the associated radius of convergence. So we'll make the same sort of table here. We're going to have the nth derivative of our function, the nth derivative evaluated at pi, and then the coefficient. So we'll have the nth derivative at pi, remember, divided by n factorial. And just do enough until you see a pattern. So sometimes it'll take more derivatives for certain functions than others, depending. Okay, I'm going to take about 6 derivatives, just in case you want to know how far to make your table. So the 0th derivative, or the original function, is cosine of x. First derivative is negative sine x. Second derivative, keep the negative, cosine x. Third derivative is sine x. And then fourth derivative gives us back cosine x, right? The derivatives are on a cycle of length 4. Fifth derivative, why not? We already have it, you can just copy from the first. Negative sine x. Sixth derivative is going to match with the second, so negative cosine x, etc. Okay, that was a little too much. Let's get rid of that. Okay, now let's evaluate these derivatives at pi. So cosine of pi, that's negative 1. Negative sine of pi is going to be 0. Negative cosine of pi is going to be 1. Then we get 0 again. So it repeats. Negative 1, 0, 1, 0, etc. Now what if I divide these by n factorial? So I'm going to have negative 1 over 0 factorial, which is 1. So this would be negative 1. 0 divided by any non-zero number is 0. Then I'm going to have 1 over 2 factorial, 0. Negative 1 over 4 factorial, 0. Positive 1 over 6 factorial, and then we'd get a 0. Okay, so it looks like we're losing quite a few terms here. That's why I took so many derivatives. So let's start listing them out. Okay, so f of x, which is cosine of x, is equal to, so the first term was negative 1 over 0 factorial times x minus pi to the 0. This is for n equals 0. That's from this guy right here. Plus, if n is equal to 1, I just get 0. Okay. Plus, I'm going to have 1 over 2 factorial times x minus pi squared. That's for n equals 2. Plus 0 plus negative 1 over 4 factorial x minus pi, excuse me, to the 4th. So this is n equals 3. This is n equals 4. Okay, let's keep going. We did more work than that. Plus 0 for n equals 5 plus 1/6, 1 over 6 factorial times x minus pi to the 6th. That's for n equals 6. This is for n equals 5 plus dot, dot, dot. Now notice only the even terms, the terms with an even index survive, right? So this is gone, this is gone, this is gone. So now I have negative 1 over 0 factorial. I know that's just negative 1, but I'm leaving it like that so we can write the pattern out in summation notation, okay? Times x minus pi to the 0. Then what's the next survivor? 1 over 2 factorial times x minus pi squared. Next survivor is negative 1 over 4 factorial times x minus pi to the 4th. Then I have plus 1 over 6 factorial times x minus pi to the 6th, etc. So now I want you to think of this as your new series, okay? And we could start writing it in summation notation nicely if I start at 0, right? And then this would be where n is 1, n is 2, n is 3. Okay, so I would write that as the sum, n equals 0 to infinity. Notice in the denominator, I have 2n factorial, right? Since they're all even factorials. I'm going to have x minus pi raised to the 2n, even exponents on all of those. And then I need the first term to come out to be negative. So I want negative 1 to the n plus 1. So there we go. And then now we need to find the radius of convergence. So again, we're just going to use the ratio test. So I'm going to look at the limit as n approaches infinity, absolute value. I have x minus pi. I'm already going to substitute in 2 times n plus 1 over, this is going to be 2 times n plus 1 factorial. And then let's just go ahead, multiply by 2n factorial over x minus pi to the 2n. I have absolute value of all of that. And then this is going to give me the limit as n approaches infinity. Now the exponent would be 2n plus 2. So I'm just going to have x minus pi squared left over. And then over here we have 2n plus 2 factorial. So that'll cancel with the 2n factorial, but I'll have 2n plus 2 and 2n plus 1 left over. Okay, I can take that x minus pi squared outside the limit, and I don't need the absolute value since that's not ever going to be negative. So I have x minus pi squared times the limit as n approaches infinity of 1 over 2n plus 2 times 2n plus 1. And as n approaches infinity, this quantity goes to 0. So this limit is actually going to be 0, which is always less than 1. So what does that mean? My radius of convergence is infinity, infinite. All right. That's a good one. One last example. So find the Taylor series for f of x equals 10 over x centered at a equals negative 2. And then what is the radius of convergence? Okay, so here we go. We'll make our table again. In fact, we can just kind of get going with this one. I think we're professional now. So we have f of x is 10 over x. So f prime of x is going to be 10 times negative 1 over x squared. F double prime of x is going to be 10 times negative 1 times negative 2 over x cubed. Do you notice a pattern a little bit? F triple prime of x is going to be 10 times negative 1 times negative 2 times negative 3 over x to the fourth. Do you feel a factorial coming on? And then fourth derivative is 10 times negative 1 times negative 2 times negative 3 times negative 4 over x to the fifth, etc. Now I'm going to substitute in negative 2 for a. So f of negative 2, that's going to be negative 10 divided by 2. I'm just going to leave it like that for a second. And then let's see what else we have here. So f prime of negative 2, that's going to be negative 10 times 1 over 2 squared. F double prime of negative 2 is going to be, let's see, negative, right? Because I'm going to cube it, so there's still going to be a negative 10 times 1 times 2 over 2 cubed. F triple prime of negative 2, that one's also going to be negative. So negative 10 times 1 times 2 times 3 over 2 to the fourth. Let's do the last one. So the fourth derivative evaluated at negative 2. This one's also negative. 10 times 1 times 2 times 3 times 4 over 2 to the 5th. So notice this is not alternating. All the coefficients will be negative. So keep that in mind. Okay, so now let's start writing out the first few terms of our Taylor series. So f of x, which is 10 over x, I can write it as negative 10 over 2, put a 0 factorial there, right? So I took my original coefficient, just threw a 0 factorial in the denominator, and then I have x minus negative 2, so x plus 2 to the 0. Okay, next term, also negative. 10 times 1 over 2 squared times 1 factorial times x plus 2 to the first. Next term, minus, this is 10 times 1 times 2, that's 2 factorial, right? Over 2 cubed, and then I have 2 factorial times x plus 2 squared minus 10 times 1 times 2 times 3, that's 3 factorial over 2 to the 4th times 3 factorial times x plus 2 cubed, etc. So look, we can clean this up a little bit. I can write this as negative 10 over, we'll just leave it like this, 2 times 0 factorial times x plus 2 to the 0. But the factorial can cancel out, right? These cancel, these cancel, these cancel. So really, I don't even need this anymore. It's not going to remain in any of the terms. So I'm just going to leave that as a 2. Then the next term, I can write it as negative 10 over 2 squared times x plus 2 to the first minus 10 over 2 cubed times x plus 2 squared minus 10 over 2 to the 4th times x plus 2 cubed minus, etc. So do you see a pattern? Well, I see a negative 10. I'm just going to leave that outside the sum. We can start at n equals 0 to infinity. And then notice, x plus 2 is raised to the n, but 2 is raised to 1 power higher. 2 is raised to the n plus 1. Okay, that looks good. Now can we clean this up a little bit? Okay, so I can write the denominator. This is negative 10 times the sum, n equals 0 to infinity. We have x plus 2 to the n over 2 to the first times 2 to the n. So if you want to bring this negative 10 back inside the sum, negative 10 divided by 2 is negative 5. So I can write this as the sum, n equals 0 to infinity, of negative 5 over 2 to the n times x plus 2 to the n. So there's our series. Okay, well now I need to find the radius of convergence. So I'm going to take the limit as n approaches infinity, absolute value, a sub n plus 1 over a sub n. So this is going to be the limit as n approaches infinity. I'm going to have absolute value of negative 5 times x plus 2 to the n plus 1 over 2 to the n plus 1 times 2 to the n over negative 5 times x plus 2 to the n. So let's see what cancels out. A lot of stuff. Negative 5 cancels. 2 to the n is going to cancel. And then x plus 2 to the n is going to cancel. So what are we left with? Let's see, I'm left with the limit as n approaches infinity. I have absolute value, x plus 2 over 2. Wait a minute, there's no n's. Okay, then this is a constant if you're looking at the limit as n approaches infinity. So this is just the absolute value of x plus 2 divided by 2. And in order for this series to converge, this quantity, this limit, needs to be strictly less than 1, which means the absolute value of x plus 2 has to be less than 2. So now we know our radius of convergence is equal to 2. All right, so that concludes the first part of Taylor and Maclaurin series. Stay tuned for part 2.